Okay, so now that we understand what we mean by atomic orbitals and how we can house electrons in them, they have to sit somewhere, the electrons have to go somewhere, and they're sitting in those atomic orbitals, we can now show our shorthand of that through an electron configuration. So again, the electron configuration describes how the electrons are distributed in the various atomic orbitals. In a ground state hydrogen atom, remembering that ground state means that the electron is in n equals 1 from our previous chapter. In a ground state hydrogen atom, the electron is found in the 1s orbital. There's only one electron in hydrogen. Remember, if you look in your periodic table, hydrogen is number 1. So it has one proton, one electron. And with electron configurations, we only care about the electrons. So the electron is found in the 1s orbital, 1 meaning n equals 1, and s meaning we can fit 2 electrons maximum. But since I only have one electron, we can show it looking like this. So what I have here, so I'll this in blank, is a version of an orbital diagram. Where we show each orbital as a box. I should say each orbital orientation as a box. Because when we get up to the p, we have 3 orientations, meaning we can fit 2 electrons into each of those boxes. So when we talk about orbital diagrams, this is what we're talking about, the box diagrams. So our 1 electron for hydrogen is in the 1s orbital. So we see it here as 1 arrow. So we denote electrons as arrows, specifically half arrows that it can be pointed up or pointed down. Okay, and we use this to denote the spin of our electrons. So if we think about it, if I have an orbital, okay, and I can fit 2 electrons in them, these electrons are negatively charged, meaning that they don't like each other. Remember, opposites attract, but similars repel. So what's going to happen is these electrons are going to start to spin in opposite directions because they don't want to be near each other. Okay, so as they start to spin, they're going to spin in opposite directions. So we denote that spin using our arrows. Okay, so we have an up spin and a down spin, meaning they're spinning oppositely. So we can now write a shorthand for this to show where that 1 electron is in hydrogen, and that is what is being shown right here. So we show 1, this is our n value, so that's our principal n value. The s is the type of orbital, and the superscript here is telling you how many electrons are in that orbital. Okay, how many electrons are in that specific orbital? So this overall notation, this 1s1, that is called the electron configuration. So when we're talking about electron configurations, we're going to be seeing 1s, 2s, 2p. We're going to be seeing that type of notation, which we're going to walk through here. So what happens if we excite that electron? So we talked about, if we put in extra energy, the electrons can move to a higher energy level. Okay, so if we're in an excited state where we have extra energy, the electron is going to move to an orbital of higher energy. So we're going to move, we started off in the 1s, and we're going to move that electron up to a higher energy orbital. Okay, remember, further away, those are higher in energy. That's what we talked about in our previous chapter, in chapter 3. So if we move this electron to a higher energy level, to an excited state, our electron configuration is going to change because our energy level has changed. So now instead of being 1s1, we're now 2s1. So our n value is now equal to 2, which corresponds to where it went to. It's still in an s orbital and there's still only 1 electron. We just changed energy levels. Now let's say that electron actually went to the 2p. We could write this as 2p1. It's now in the 2p orbital, so energy level 2. It's in a p orbital, and there's one electron still. Now, because there are 3 orientations of the p orbital, we can't tell exactly which one it is, so we don't show any notation like x, y, or z. We can just show it as 2p1, and we know that it's in one of the 3 orientations of our p orbitals. Okay, now one electron is nice and easy because there's only one of them. They don't interact with anything. There's no other electron for it to interact with. But obviously the remainder of our periodic table has more than one electron. So we have to generalize our idea of our electron configuration to the remainder of the periodic table, where we have multi-electron atoms, so more than one electron. More than one electron atoms. So what happens here is our orbitals start to split. So what we saw before was all of these were on the same energy level right next to each other. But now when we're trying to accommodate more than one electron, in order for these orbitals to be energetically favorable, they have to split. Okay, this is going to become important when we start writing electron configurations for larger atoms, which may get a little confusing. So you just have to remember that these trends that we're going to see come out of this splitting. Specifically, we start to see splitting get confusing in this region, where we go from 3s to 3p, but then all of a sudden this 4s comes down in energy and the 3d comes up in energy. And that's because it takes the 3d, since there's 5 orientations, there's a lot more energy in those orbitals in comparison to this one orientation orbital. So the 4s is just more energetically favorable than the 5 orientations of the 3d. And we see that throughout the entire periodic table. Okay, now when we do start to introduce more electrons, we have to follow specific rules about how we're showing those electrons, where we're showing those electrons going. They don't just go into any orbital in the entire atom. They go into specific orbitals and they orient themselves in very specific ways. So the rules that we're going to discuss are very specific to how we are going to build up these orbital diagrams in our electron configurations. So the first rule is the Pauli exclusion principle. And this states that no 2 electrons in one atomic orbital can have the same spin, as we would not be able to tell them apart. So in order to tell electrons apart when they're in the same box, in the same orbital, so remember when we're talking about orbitals, we're talking about one individual box. In order to tell those 2 electrons apart, they have to be spinning opposite from each other. Remember, because they repel each other because they have the same charge. So here I have hydrogen. And then let's say we move on to helium, where we add one more electron. So we're going to add that electron first to the 1s, because that's our lowest energy. We always want to go from low to high energy. So our electron is going to add to the 1s, but we're going to show it having a downspin. So we started with an upspin over here, and now those 2 electrons are going to have an upspin and a downspin, because when they're in the same box, they can't have the same spin. So when we show them in an orbital diagram, we show them with 2 opposite half arrows. Okay, we do the half arrows to show the electrons, okay, and we show them as up and down half arrows. So that's the Pauli exclusion principle. No 2 electrons can have the same spin so that we can tell them apart. Okay, now what happens if I want to add another electron? So we'll go on to lithium, add 3 electrons. Well, we then follow the Aufbau principle, which states that electrons are added to the lowest energy orbitals first before moving to higher energy orbitals. So when we started with helium, we were in the 1s, And now if I wanted to add one more electron, again, like I said earlier, they don't just go into random orbitals. So it's not like I could just put an electron there and say, yep, that's lithium. That is not true. So the next electron would go into the 2s because 2s is our next highest energy orbital. Okay, so we fill from lowest energy to highest energy. Okay, so we're going to put that extra electron, or that next electron, in the 2s orbital. Now, continuing on with the Aufbau principle, here we have lithium. We just looked at this one. Then we have beryllium next up. And when we add that one electron, we're following, again, the Pauli exclusion principle, where that electron is going to be added to the 2s, but now have a down spin. Okay, so I had an up spin here. I now have an up and a down spin because two electrons in the same orbital cannot have the same spin, so we can tell them apart. Okay, so I add one more electron to go to beryllium, and I follow my Pauli exclusion principle. Then when I go from beryllium to boron, okay, so now I have 5 electrons that I'm dealing with. I'm adding in one more electron. Okay, that electron now is going to go into the 2p. Okay, because the 2s is full, can only hold 2 electrons. Now I'm going to go to the 2p because that's our next highest energy orbital. So that electron from boron is going to be in the 2p orbital. And typically, just the shorthand of it is we show it in the first box first, so we fill up our first orientation before we move on to the next orientation. Okay, so we typically show it in the first box. Now to make a note about our electron configurations, which are down here on the bottom, okay, so we have our orbital diagrams on the top and our electron configurations on the bottom. So here are our orbital diagrams. And here are electron configurations. Okay, we see that with each new electron, we're still keeping the previous orbitals in our electron configuration because our electron configuration has to show where all of the electrons are. So lithium has 3 electrons, 2 of them are in the 1s orbital, and 1 of them is in the 2s orbital, which is what we see in the orbital diagram. Then when we add one more electron to go to beryllium, we now see that we went from 1s2, 2s1 to 1s2, 2s2, because now I have 4 electrons. So our superscripts here, if we add them up, they equal our number of electrons. Okay, so that's always a good way to check your work, to make sure that you have enough electrons in your electron configuration. Now, when I go from beryllium to boron and I add 1 extra electron, well, my 1s and my 2s, we can see that they're filled up. So the next possible place to put my electron, my 5th electron of boron, would be in the 2p. So my electron configuration becomes 1s2, 2s2, 2p1. And like I said earlier, we don't denote our orientation in any way. We just know that it's in one of those orientations. So we just keep it as 2p1. Okay, so our Aufbau principle tells us that we have to fill our energy levels from lowest to highest energy. Our final rule is Hunds rule, which states that the most stable arrangement of electrons is the one in which the number of electrons with the same spin is maximized. So spin being, positive or negative spin, our little up and down arrows, we want to maximize those to be the same. So here we have carbon, which is right after boron. So I now have 1s2, 2s2, 2p2. Carbon has now 6 electrons. So I added one more to my 2p. Now I could have, let's cover this up real quick. I could have added the electron there, okay? But based off of Hunds rule, that would not be maximizing the spin. So in order to maximize the spin, we want as many electrons to have the same spin as possible. So if we look at it this way, we have 3 electrons that are having a positive spin and 3 electrons that have a negative spin. Whereas if I do it the other way, that follows Hunds' rule, if I erase what I covered up, I now have 4 electrons with an upspin and 2 electrons with a downspin, meaning that this is the most maximized orientation of those electrons. Those electrons don't want to pair up if they don't have to, okay, and that's also kind of Hunds' rule. So let's say electrons will not pair up unless they have to. When I was learning this in chemistry in high school, my teacher made a really nice comment about this, and she said Hunds' rule is like when you're getting on a school bus. You each sit in your own seat until there's no more empty seats available, then you have to start pairing up. Electrons do the same thing. So we put electrons into the boxes with the same spin first, and then we only pair up when we don't have any orbitals left that don't have any electrons in them. So electrons will not pair up unless they have to. So let's move on from carbon to nitrogen, and then nitrogen to oxygen to show that. So here we have carbon, here we have nitrogen. Okay, so we're adding 1 electron. Okay, so that the next electron goes into the last spot of the 2p. So I now have 1, 2, 3, 4, 5 electrons with an upspin, and still only 2 electrons with a downspin. So my upspin, or the same spin, is being maximized. However, our rule also says that electrons will only pair up unless they have to. So when I add 1 more electron to go from nitrogen to oxygen, that 1 electron is going to now follow our Pauli exclusion principle, and it's going to add to our 2p, but instead be in a downspin. Okay, so following Aufbau and also following Pauli exclusion, we still have to fill up our 2p, okay, before we can move on to any other energy level. But so that's Aufbau's principle, that we have to fill up, go lowest to highest energy. The Pauli exclusion principle then tells us that that spin has to be an opposite spin, so we're going to do downspin, which is opposite of our upspin. This is still following Hunds' rule because I now have 5 electrons with an upspin and now 3 electrons with a downspin. So I'm still maximizing how many electrons have the same spin. And then we can just look at our electron configurations again. So down here, we're just adding those electrons now to our p orbital. So we have 1s2, 2s2, 2p2 for carbon, and then that p becomes 2p3 in nitrogen, and then for oxygen it becomes 2p4 because we've added additional electrons. And again, because there are 3 orientations of p orbitals, I can fit a maximum of 6 electrons in those p orbitals. So at some point this is going to become 2p6, which we'll see in some of our later examples as well. Okay, so let's do a quick practice on our principles and our rules. What rule or principle is violated in the below diagram? So I have 1s, 2s, and 2p. So right now our electron configuration is looking like 1s, 1, 2s, 1, 2p, 3, because I have 1 electron in my 1s, 1 electron in my 2s, and 3 electrons in my 2p. Okay, so let's think about what principle or rule is being violated. Aufbau, Pauli exclusion, or Hunds' rule. Okay, so if we think about our rules, Aufbau says that we have to fill lowest to highest energy. Pauli exclusion says that 2 electrons in the same orbital, or in this case box, can't have the same spin. And Hunds rule tells us that we have to maximize spin. So this is about pairing up. Okay, so let's see. Let's go from the bottom. Maximize spin. Well, all of them have up spins, so that's pretty much maximized. So I'd say this is not a violation of Hunds rule. Okay, Pauli exclusion principle says that 2 electrons that are in the same orbital can't have the same spin. Well, there's no orbital that has 2 electrons, so it's technically not violated because they all have 1 electron in them with 1 spin, so we can tell them apart. Aufbau principle says we have to fill from lowest to highest energy. We know that 1s is our lowest, then we go 2s and 2p. So we didn't fill up our 1s before moving on to our 2s, so we would be violating Aufbau's principle because we didn't fill our boxes before moving on to the next one. So what this should look like is we have 1s, 2s, 2p. We have 1, 2, 3, 4, 5 electrons to work with. So we do 1, 2. Okay, we filled our 1s. We're following Pauli exclusion because they have different spins. So we filled our lowest energy. Now we move on to our next one. So then we have 1, 2, which again, we follow Pauli exclusion by giving them opposite spins. And then my last electron is going to go in my 2p, which is my next highest energy level. So that's what our orbital diagram should have looked like.